Hold on to your nerves. No, we'll try to. All right, now what I'm going to do is I have slides from this new book on it's called Engineering Software Products by Ian Somerville. He's like a old professor who wrote the classic book on architecture, but he just wrote this new book, and I think this new book it's shorter and I think it's better. So I want to go through hopefully the whole book with you guys. But I'm starting at chapter 5, I think, and maybe we'll go back to the beginning, but because it's chapter 5 is also about architecture. How do I, oh. No. Yeah, okay, software architecture. You need to pay attention to architectural design, which includes, if you want to make good software, reliable, secure, and efficient. Notice these are 3 carefully chosen words. Reliable means that it won't crash. Secure means people won't hack it. And efficient means that it'll work quickly. You need to pay attention to its overall organization, how the software is decomposed into components, the server organization, which is what we talked about before, the technologies that you use to build the software, the architecture of the software product affects the performance, usability, security, reliability, maintainability. Okay, the technologies. Now, what, you're going to use Java, you're going to use C++. So, one might be faster than another. There are many different interpretations of the term software architecture. Some focus on architecture as a noun, the structure of a system, and others consider architecture as a verb, the process of defining. See, I would say it's the verb. I would go more with the verb. In other words, how do we design? How do we create the architecture? Architecture is the fundamental organization of the software system embodied in its components, the relationship to each other and the environment, and the principles guiding its design and evolution. Okay, you could spend an hour discussing what the definition of architecture is. A component is an element that implements a coherent set of functionality or features. In other words, a component has to do something. It can't be too small so that it doesn't actually provide any functionality. It provides some functionality. So we're defining the words architecture and components. Software components can be considered as a collection of one or more services that may be used for other components. In other words, there's reusability. Software components. You can use this component twice in 2 different systems. When designing software architecture, you don't have to decide. No, doesn't want to stay there. You don't have to decide how an architectural element or component is to be implemented. In other words, you can just define what components I'm going to need. I'm going to need something that does sorting. I'm not going to define exactly if it's bubble sort or quick sort. Rather, you design the component interface and leave the implementation of that interface to a later stage of the development process. In other words, you can be, as the architect, you can just design what components you want, and then you can tell a programmer, you go and write the inner workings of this component. In other words, if you work for a big company like Amdocs or other companies, you'll end up writing pieces of software that you have no idea what the purpose of, why you need this. You're just given a document that says it has to get this input and this output, and you just do it. And it's the architect who knows why you need this system. And you'll work on a certain piece of software, for a year and never have any idea how the system works. You'll just know how to do your little part. Then you're a programmer and you're not an architect. The architect, of course, will have to know what the components are and how to put them together. So services accessed directly by other components, but you can also have services accessed through some API. Or you can expose the components. Or no, you have two different components. You can access these. You can access the components, their services directly by accessing the component, or you can access some kind of API which itself accesses a component and then gets the services from it. So a component can actually provide multiple services according to this. Why is architecture important? It has a fundamental influence on the non-functional system properties. Where's table? In other words, all these things. It affects the responsiveness, reliability, availability, security, usability, maintainability, and resilience. Resilience here he defines as that if part of the system stops working, will the rest of it keep working? As opposed to reliability. Does it behave the way the developers intended it and the way the users want it? So architecture is important because it affects those things. As if you have a bad architecture and something fails, think of one example of architecture you can think of is the internet itself. Who developed the internet? What organization?
Was it DARPA, perhaps? DARPA.
DARPANet. Yeah.
DARPANet.
Yeah, DARPA. But also, my answer I was thinking of is the DoD, the Department of Defense. And what was the idea? What is the fundamental architecture of the internet?
I mean, I think it's a series of tubes, no?
A series of tubes? I don't know. Anyone else?
Wasn't it just like a email service?
It's a haircutting service. It provides haircuts if you need them. Email service? No. The fundamental architecture. What I mean is it peer-to-peer? It's peer-to-peer, first of all.
It was.
It's a mesh. The word I'm looking for is mesh. It's a mesh.
Web,
it's not a mess, it's a mesh. What is a mesh? A mesh means that every point is connected to every point around it. So that what the idea was that if there's nuclear war, and let's say the center of the country gets wiped out, there's nothing there, no electrical systems. I still want from Washington to be able to talk to California. So the idea is that if a section of the country gets wiped out by nuclear war, the communication routes will automatically find another route to go. By having, instead of I don't want a direct line from here, I don't want everything to go to a certain town in Washington, in Ohio, and then from that town, everything goes to, that would be one focal point, everybody got to go through Ohio. Then all the Russians have to do is blow up Ohio, and, we can't communicate. So the idea is that there's multiple paths that architecture essentially provides resilience. And that's what they were looking for in the Department of Defense. It's a communication channel that is very hard to sever because there's many, many routes to get from one place to another. And it's a mesh system. So architecture can help. If you do the right architecture for your needs, then it will, provide you with those things in the next page. Architecture design, understanding the issues that affect the architecture of your product, creating architectural description that shows the critical components and their relationships. Okay. Minimizing complexity should be an important part of, right? You don't want complexity. You don't want it to be overly complex. It'll be difficult and expensive to understand and to change later. If you make a mistake, go find it. You want your system to be as simple as possible. Programmers are more likely to make mistakes when they have a complex system. So these are the goals: security. I think these are mostly explainable, self-explanatory. Availability, if everybody's trying to access, because I was on television last night, like I said before, the system should be available even when there's lots of requests. Maintainability, a lot of people forget about maintainability. Can you change features without having to rewrite the whole system? The influence of architecture on architecture of system security. a centralized security architecture. In the Star Wars sequel, Rogue One, the evil empire have stored the plans for all their equipment in a single highly secured, well-guarded, remote location. This is called a centralized security architecture. It is based on the principle that if you maintain all of your information in one place, then you can apply lots of resources to protect the information and ensure that intruders can't get in. In other words, if you have this problem, like if you have, let's say you have a collection of expensive watches. So you're afraid that you put them all in your safe and lock them in the safe, or do you put one like under your bed and one under a cushion and one inside of a book, and you spread them all out of your house. So if a thief comes in, he might find one, but he won't find them all. Or do you put them in a safe? Then it's like all or nothing. Either he won't break into the safe or he will. So unfortunately for the Empire, the rebels managed to break the security. They stole the plans for the Death Star, an event which underpins the whole Star Wars saga. In trying to stop them, the Empire destroyed their entire archive of system documentation with who knows what results and costs. In other words, I guess I don't remember, but they blew up something. Had the Empire chosen a distributed security architecture with different parts of the Death Star plans stored in different locations, then stealing the plans would have been more difficult. In other words, if you would take your watches, even worse than what I did, take them apart and put like different pieces of them in all different parts of your house, then first you have to find all of them. And if you found one, it would do you no good. But then you'd have to have multiple copies of each piece. So in case you lost one, you would still have another copy. The rebels would have had to breach security in all the locations to steal complete Death Star blueprints. Okay, so you can have a distributed or centralized security architecture, and both have their merits, I think. The benefits of centralized security, that's easier to design and build protection. I mean, what are we talking about security? Your source code. Where are you going to keep your source code? You got to have your source code somewhere. That's not really architecture, but let's say you have, your databases that stores all your critical company information. It takes longer to access all the information and it costs you more to protect it if you distribute the information. In other words, if I want to get the information, just go to one place. It's going to be fast and efficient. If security is breached in one location, you lose the information that you've stored there. In other words, like I said, if a guy breaks into your safe, then everything's gone. So that's centralized security. User interface, C1, C2, shared database. So in that picture we just saw, it has two components, component 1 and component 2, that share a common database. Right? There's a shared database, and they both use it. Assume C1 runs slowly because it has to reorganize the information in the database before using it. The only way, in other words, C1 has to do all kinds of changes to the database. The only way to make C1 faster might be to change the database. This means that C2 also has to be changed, which may potentially affect its response time. In other words, they're both using the same database. So if I want to change the database to improve the performance of one of the components, I'm going to have to rewrite the other component. They're all dependent. It's kind of like a centralized focal point of information that causes the changes of this one to affect the changes of this one. I mean, it could potentially. So you see, you could have a system like this where each one has their own database. Of course, that's going to be weird. What, the databases are going to be designed differently? That's also kind of weird to me. So the different architecture, each component has its own copy of the parts of the database that it needs. If they have different parts, what if they have overlapping parts? Then what are you going to do? But if they each have their own separate parts, if one component needs to change the database, this does not affect the other component. So you want to have, I mean, the truth is you want to have, I don't know, did you do a course on databases?
Some yes, some no.
So what, well, since you're the only participant today, as far as I can tell, well, Yona was here. What, there's Yona. I don't know, these other guys, they just,
You have other people here.
Third years have done the course and second years are currently doing the course. That's the
okay, but so who has done databases? Raise your hand. Okay, so Daniel, what is the fundamental idea of databases? The fundamental, if you could put it in one thing, one idea that you learned from the course, if anything, what would it be? And no
Like
jokes.
you cut out for me something before one idea. You just cut out. What was the first part you said?
Oh. What is the one major takeaway from the course?
For database?
Conceptual,
What's it?
conceptual takeaway.
Ooh,
Yona.
yeah. Redundancy is bad.
Ah, there you go. That's what I'm saying. Right. Redundancy is bad. That was what I would say.
Well, I would say make sure that it's stuff is at least in third normal form. That's my
Yeah, something like,
takeaway.
yeah, that's too technical.
Because
for me.
that includes redundancy and all that stuff.
Yeah. The idea is that if you have, let's say, here's my classic example. If you have, for example, a database with
Always
clients.
back up your database. That's my second thing.
Clients, you have clients in your database with all their information, and you have books in your database. So what is an order? An order should have in it a reference to the client number
And the book.
and the book number, not the book title, not anything about the book, just the book reference number. The books database is just all books. That's all it is. But an order has a reference to the two of them, plus, a quantity and a date. So you try to keep each database that has exactly, information about one thing. And you don't create, so of course, this kind of example that he gives here, that each one should have its own database, is kind of hard for me to understand because, well, is that really going to happen so much? I guess occasionally it'll happen, but sometimes you'll have a component 3 that needs to use both databases. I would say most of the time. But by separating as much as we can, then if I need to rewrite component, if I need to reorganize the database so that component 1 will work faster, then I can do that independently of component 2. If one component needs to change the database, this does not affect the other component. However, a multi-database architecture may run more slowly and may cost more to implement and change. You have drawbacks. A multi-database architecture needs a mechanism, component 3, to ensure that the data shared by C1 and C2 is kept consistent when it is changed. In other words, if there is overlapping data, which there presumably will be, I need a person to maintain that. I need some kind of system. Usually that would be, if you have a mirrored system, right, these are not mirrored systems because the organization, the whole point is the organization of these databases is different or could be different. Okay, fine. That is showing you the idea of centralization and decentralization. So issues that influence architectural decisions. Software compatibility. We may want to make our system compatible to a previous system. Number of users. We may design it in a certain way based on how many users we expect. Reuse. We may want to, after we've developed our software for our company, we may want to sell it to other companies that need similar software. So we may want to design it. That's a very important point. That a lot of times happens. Companies, they create software for themselves, and then their companies, they find out they're not making very much money doing what they're doing. So they say, well, we've written all this software. Maybe some other company could use it. So now, but they say, oh, but our software is too proprietary. It has so many things that are built in for our company that nobody else would want. So you really should make your software have like a generic element to it, and then modification element that can be decoupled. So you can sell the parts of it that are not proprietary, that are not, only for your company. Product lifetime. In other words, you should think about product lifetime. How long are you going to want to use it? If it's only one-time use, then maybe you'll design it differently. Non-functional product characteristics. Not sure what they mean by that. Here, non-functional product characteristics. Non-functional product characteristics such as security or performance that affects all users, but they're not part of the product. They're just like, I want it to be secure also. If you get these wrong, your product is unlikely to be a commercial success. Unfortunately, some characteristics are opposing, so you can't optimize. So you can only optimize the most important. Okay. Maintainability versus performance. System maintainability is an attribute that reflects how difficult and expensive it is to make changes to a system after it has been released to come out to customers. You improve maintainability by building a system from small self-contained parts, each of which can be replaced or enhanced if changes are required. In other words, it's usually faster. You see this in kernel design. A single kernel, everything in one location is going to run faster than having lots of parts. But it may be harder to maintain because you have to understand a large system in order to change anything. If you have small components, then you just have to understand that component to change it. So maintainability is easier when you have components. In architectural terms, this means that the system should be decomposed into fine-grained components, each which does one thing and one thing only. However, it takes time for components to communicate with each other. Consequently, if many components are involved in implementing a product feature, the software will be slower. In other words, you make it too granular, it can also be not good. But granularity helps for maintainability. That's the point. Also, security and usability. If I make everybody change their password every 3 days, then it's harder to use the system. But I have more security. An attacker has to penetrate all the layers of security of a system. So we may have multiple layers of security. So I think I have a picture of that here, yeah. So in other words, think about this. In order to use some certain database, to get to certain data, first you have to, be from a certain IP. Only certain IPs can access my server. I have a list of my workers and their IPs can access it. Everyone knows what an IP is, I assume. Then we have application authentication. As once I've gotten to access to the server, I still have to log in. Then if I want to use a certain feature, maybe I have to provide another password. Then the data itself that I want isn't stored in plain text. It's stored encrypted. And then I don't know what this last level is, but the point is I can have the data encrypted, even if he's got in, somehow he got the wrong, he spoofed the IP and he got this password. He still has to get this password. And even if he gets in, the data itself is encrypted. And so he can only access, through my software. He can't like download the whole data because it's all encrypted. So we can have levels of the layered approach to security affects the usability of the software. Users have to remember information like passwords. Their interaction with the system is inevitably slowed down by security features. And people try to look for workarounds so that they do not have to re-authenticate. The famous example is the Post-it on your computer screen with all your passwords on it. So then some guy walks into your office and can access everything because he sees your passwords on the Post-it on your screen. So passwords don't actually help necessarily. To avoid this, you need an architecture that doesn't have too many security layers. It doesn't enforce unnecessary security and provides helper components that reduce the load on users. In other words, don't overdo your security, but you need to have a lot of security. So that's a trade-off between security and usability. Now there's a trade-off between availability versus time to the market. Availability is particularly important in enterprise products, such as products for the finance interest rate. In other words, it needs to be available all the time. Actually, I have a bank account in America, and at a certain time on Sunday in the middle of the night, I can't access it. Now, I know why. I can guess why. Why would you guess?
Are they updating stuff?
Right, they're updating their database. So those moments I can't access, even though it is a bank. But actually, it's kind of weird. I mean, you never would imagine that like Amazon at a certain hour, you can't buy anything. That would be insane. How do they update their, how come my bank needs to, I mean, I don't understand why my bank needs to update and close the system down and the Amazon doesn't. They both have sensitive information.
You need to reroute the traffic to a different server and then update that and then kind of swap it.
Right.
I
Why
think your
can't my
bank
bank do that?
does
My bank is like one of the largest banks in the
Not a
world.
tech company. They're a bank.
What?
They're not a tech company. They're a bank. Maybe that's.
Yeah, I guess so. It's kind of funny though. I mean, in this day and age, they can't find a tech person. I mean, they
Which
They have-
bank?
Offer your services to this company.
Okay.
Which banks do I know to stay away from?
Availability is normally expressed as a percentage of the time that a system is available. Okay. Architecturally, you achieve availability by having redundant components in the system, just like Yoni said. Of course, it doesn't always work. You understand the problem. If I need to, in other words, I don't know, there's a certain problem, like I can't let the database being updated while I'm backing it up, maybe. As if depends how the backup system works. Anyway, to make the use of redundancy, you include sensor components that detect failure and switch components that switch operation to a redundant component when a failure is taken. I actually worked at Machon Lathe. They had at one point disks that they probably still do, that you could pull out a disk from the machine and disconnect it from every connection and have no effect on the services provided.
Well, it
There's that
depends. What rate is it in? You can
Exactly.
do that with one of the rates. You can have multiple disk failures at the same time, and the system will still run.
Well, that's what I'm saying. This is a rated system. If anybody doesn't knows what RAID is, but RAID is just a way of having disks connected in parallel so that, well, there's different types of RAID. But the point is, they had a system where I did it. I pulled out a disk from the machine and it had no effect, and I could put it back in because there's redundant disks. But you have to have a sensor to notice that this disk is no longer accessible. Use the other disk. Implementing extra components takes time and increases the cost of the system. It adds to the complexity of the system and therefore increases the chances of introduction of bugs and vulnerabilities. In other words, redundancy can cause errors and can cause vulnerabilities. You have now one more system to protect. Architectural design questions. How should the system be organized as a set of architectural components where each of these components provides a subset of the overall system functionality? In other words, okay, fine. You've explained to me I need components. How the heck am I going to figure out what the components are going to be? The organization should deliver the system security, reliability, and performance you need. But how should these architectural components be distributed and communicate with each other? What technology should you use in building system and what components should be reused? Abstraction in software design means that you focus on the essential elements of a system or system components without concern for its details. So you're going to first focus on like what you think are the essential things that your system has to have as elements. At the architectural level, your concern should be on large-scale architectural components. Decomposition involves analyzing these large-scale components and representing them as a set of finer grain components. So first you figure out what your main components are, then you figure out what their subcomponents are. Okay, so what do we have here? An architectural model of a document retrieval system. So these are the components. These are each one of these boxes components, and the inside of them are the subcomponents. A web browser can do different things. It might provide printing. In other words, you can print the document, put it into a format that, PDF or something that can be printed, changing it from the web's version to a printable version. It can also make sure that the inputs that are provided are valid. It can also let the user give input. User interface management, form and query manager, web page generation, document and index management. Fine, all right. Basic services, database query, query validation, logging. Logging means like what queries have been done. We want to not only to do the queries, we made a log, a list, a history of all the queries that have been done. User account management. All these are in basic services. Okay, and then the different databases might be in a database section. Complexity in a system architecture arises because of the number and nature of the relationship between the components of that system. When decomposing system in components, you should try to avoid unnecessary software complexity. So it's saying, like, on the one hand, decompose, on the other hand, not too much, because it'll cause complexity. If there are relationships between components A and B, these are easier to understand if A and B are defined in the same module, right? If A and B are always talking to each other, then maybe they're in the same component. Reduce shared dependencies, where components A and B depend on some other component or data. Complexity increases because changes to the shared component mean that you have to understand how the changes affect A and B. In other words, dependencies are problems, basically, because that means that I can't change C without understanding A and B, because I might affect A and B. I have to change C in a way that A and B will continue to work, because they're both using C. So dependencies are should be obviously you can always have dependencies, but they have to be as limited as possible. It's always preferable to use local data wherever possible to avoid sharing data if you can. Okay. So here are different kinds of relationships. So these two are both together in the same component. This component uses this component is part of this component. Fine. Separation of concerns. Organize your architecture into components that focus on a single concern. Oh, I think we should, when do we start Unix? 5, right? Let's see. We got a lot more. Okay. Separation of concerns. Organize your architecture into components that focus on a single concern. In other words, like user management, database management, document production, logging, security. You can have sections that deal with a single concern. Design component interfaces that are coherent and that change slowly. Right, there should be some kind of stable interface that you don't expect to have to change all the time. Implement once. Avoid duplicating functionality at different places in your architecture. Right, if you have a certain logical component that does some logical process, try to have it only once in your system. Don't have it say, oh, this component needs it, that component needs it. So then try to make a separate component maybe that just does this logic that each one can use. Design guidelines and layered architecture. Each layer is an area of concern and is considered separately from other layers. The top layer is concerned with user interaction, the next layer down with user interface management, the third layer with information retrieval, and so on. So that's what we were talking about with the MVC, having layers. User interaction, then interface management, that was what we called control. And the third layer is retrieval, that might be model, right? View, control, model, or model, view, control, whatever. This is the view, the user interaction. Within each layer, so that's already a way to divide up your system. Say, well, is this activity more concerned with displaying information, with providing the user with information, or is it the fundamental storage of the information? Within each layer, the components are independent and do not overlap. That's the whole point of the functionality, is that that one is independent of the other. That I can change one and I don't have to change the other. I can change the view and keep the same model, the same data model. The lower layers include components that provide general functionality, so there is no need to replicate this in the components in the higher level. Right, if I need to sort something, I may have a sort function in the data level. I'm not going to write that in the view level, even though it's related to the view. He clicks on a button that says presented to me sorted backwards, then but the view, that's the view is going to not do that. It's going to give him the option of choosing to do that, but that request will eventually get down to the lower level of the data level, of the model level, and will there perform the sort. Maybe. The architectural model is a high-level model that does not include implementation information. Right. You don't say how to do it. You just say how it's going to be designed. Ideally, components at level X should only interact with the API of the components, with the APIs of the components of level X minus 1. You see that's a point, an interesting point what he's saying here. In other words, a certain level should only relate to the level beneath it and not to its parallel levels. In other words, there may be three components in the view. Not a view shouldn't call another view, right? One view component shouldn't use another view component. All right, let's stop here for today.